Siplast is the partner you trust. To be there when the plans roll out and the ribbon gets cut. To start things off right and help when things get rough. To share experience and work side by side. We're the team you want when it has to be right. The team to help with your biggest roofing and waterproofing challenges. Whether the building houses the irreplaceable, business critical, life critical, or simply precious. We're Siplast, and we understand. It's not about the roof. It's about what goes on underneath it. Siplast. We're with you every step of the way.
Okay, everybody, thanks for joining. This is our first tour of the RISE facility. I'm Kirk Gooderham, Director of R&D. We're going to step you through, unfortunately, you can't be here today, so we're going to step you through via video. Our staff is going to walk you through some of the capabilities of the RISE Center, give you a virtual tour of the facility and the people that are working to make our products, better every day. Zach, you want to introduce yourself?
Yeah. Hey, everyone. My name is Zach Taylor, and I'm the R&D lab manager here at Siplast. I oversee all R&D projects. This includes anything from new product development all the way to raw material qualifications. And I also serve as technical support for my sales and field teams as well as customers.
And hello, everyone, and thank you for joining us. My name's Todd Corley. I'm the Compliance and Quality Control Manager at Siplast. My primary focus is on the building codes and approvals and testing Siplast systems for wind, fire, and hail. Thank you for joining us.
And I'm Jennifer Keegan, Director of Building and Roofing Sciences. This team is deeply involved with industry, conducting research, publishing papers and technical articles, hosting workshops, and provides support to the design professionals on roof system design and performance. Thanks for joining us.
We'll be your host for today, just kind of in between videos, give you some commentary and answer any questions that you may have.
And if you have any questions during the presentation, please use the chat feature to communicate with us. And if you have any technical issues, the chat will work too, and Lainey's behind the scenes and she'll try and get you worked out.
Okay, thanks, Jen. All right, let's get started.
Welcome to the RISE Center here at Siplast. RISE is an acronym, stands for Research, Innovate, Support, and Evolve. RISE is really the culture that Siplast started with. If you think about research and innovate, in the 60s we developed SBS in Europe. In the 70s we brought it to the US. In the early 2000s, PMMA, we brought that technology to the US, began producing in 2006. And that really has been the core of our business ever since the beginning and ever since I've been here. The RISE Center itself is a place where people can come to learn. You can come to see presentations. We have a demonstration building where people can play with materials, products, see demonstrations, but also get your hands dirty and play with the products themselves. We have a staff of brilliant scientists that are engaged in R&D and innovation. The RISE Center really equips them with the tools to accomplish their tasks, create new products, and offer solutions to customers. The laboratory is outfitted with some of the state-of-the-art equipment. We formulate here in the lab, we do material testing here in the lab, we do chemical analysis in the lab. All these tools and pieces of equipment really are just support functions to help our customers and consultants. We really start from infancy all the way to maturity. The scientists will develop an idea, they may look for patent applications, they'll formulate those products, but then also they take them to the operations, production, how do we manufacture those products? And also we'll take it to the field, how do they apply those products? That's key to all formulations. It's not just creating a product here in the lab. Our users, our consultants, our contractors have to be able to apply those. It needs to support their reputation in the field and for long-term applications. So our scientists work closely with our contractors, customers, our consultants and architects to create solutions for their needs.
The RISE Center is more than just a lab. It truly is an innovation center, education center. Hopefully soon, one of these days, you can get here in person and see the people, see the facility, tour the manufacturing site, and listen from all the people on the panel here from an educational point of view.
Yeah, so let's jump in here and take a look at some of the day-to-day work that goes on at RISE. Kirk, Jennifer, Todd, and myself will join you in between the video segments to discuss, and we'll really be discussing how our day-to-day supports you and your projects in the field. And if you've attended any previous Pro Series event or been fortunate enough to come to a Siplast plant tour, you know where our story begins, and that's with our blend.
My name is Daniel. I'm the asphalt chemist here at the Research and Development Lab in Siplast. Basically, I work on blend evaluations. So I make core blends, study them, evaluate them to see if I can, improve the properties. That way, whenever it goes to the big plant production, we can move it and scale it up. So I do a lot of various tests, first with the mechanical properties. So over here right now, I've just poured my first blend, which is just, whenever I make the blend, I pour it out. And I also study the mechanical properties in various ways. So over here, we have the sweat test, which can help determine the composition of our binder after mixing. So normally I put it in an oven for 24 hours, then look at it in a scale to determine how good the mixture of my binder is. This here is for the vertical flow. We try to study the load on a vertical flow for the blend in this case. Over here, we do a percent recovery where I can pour it to reach a certain percentage, normally above 1000%. And if it reaches it, and after I put it back in a water bath and test it later on, if it comes back to its original length, or at least close to that, then we can say that it has a good percent recovery for the blend. Over here too, I'm gonna do some penetration tests. So, we have one at 25 degrees Celsius and 50 degrees Celsius. These just help for the bitumen to test the hardness or softness, telling us how good our bitumen is. Over here too, we have the softening point, which is a ring and bore test. So it basically tells you, what temperature, you can heat your binder to, which is still good for various applications. And finally, we have the viscosity test, which will also test the fluidity of the bitumen at certain temperatures. So now I do it at an increasing temperature rate from 170 to about 220 degrees. Then I study the viscosity to see then how good my bitumen is. So all of these tests I'm doing here are all mechanical properties tests, which in terms of when I test the sample, if it passes the Siplast specifications, I can take it, then I'm moving on then to the director, where we can go and do then production trials and bigger trials to see then if you can take the product to market. So after I prepare my blend, one of the tests I do is a UV microscope analysis, and I use a fluorescence microscope because it emits light. So in this case, as you can see in my image over here, once we have the blend, we try to look for a distribution of the polymer. If we have a uniform distribution, it can help tell us that we have a good blend. And this relates to the viscoelastic properties of the sample. A good distribution shows that we have a good polymer. Then if a bad distribution or some bugs in there, it shows that maybe the blend is not well mixed. Over here, we have two blends. One here shows a more smoother distribution. This one here is well distributed, but as you can see, it's a little bit not as smooth compared to the SA blend on the left. Some factors may include, the mixing time, the mixing temperature, all those different things. So that's why, based on how we see the blend, we can then try to see if we can adjust, increase the temperature or mix the blend more to make it more uniform. Polymer loading can affect that too because, based on the type of polymer you have, it can increase the properties. But if you don't put a lot of it, then maybe you don't have enough of the polymers you need. Because especially for the radial polymer, it helps to know with the temperature increase in this case. But if you don't have enough polymer in there, you must see that your blend is not well smooth or mixed.
So just real quick, Daniel is our asphalt chemist here at RISE, meaning he is responsible for modified bitumen R&D work. Daniel has a PhD in applied science, but unfortunately he will not let me call him Dr. Daniel. He has a great sense of humor and fun to work with, and we look forward to seeing him grow as a scientist here at Siplast. Now, Todd, Daniel had a lot of tests going on there, and you worked in QC many moons ago. What was your favorite test?
Thanks, Zach. I'm not sure if you're alluding to my experience or my age, but it's as interesting as all of those are. The elongation recovery has to be one of my favorite because it's just so simple. You stretch the SBS out 1,000%, and you see it come back to its original form. And that's where the ASBA stick originated, which is a tool that our sales guys have used for years and still use to this day. And they essentially perform that test in front of the customer. So it's just a great test for me.
And I thought the dispersion test was really interesting. So looking for the consistent distribution of the polymers throughout the blend to determine if we need to make adjustments during production.
The dispersion, if you've ever listened to me talk, I've probably showed you lots of pictures of yellow blobs on the screen, but dispersion is really a great way to tell if the polymer's dispersed properly. And SBS is difficult because you're dealing with bitumen, which is a natural occurring material. So that consistency is difficult. And I think Siplast has always done that well. The other part is making sure you have enough SBS in there, not put too much filler in it. That's really what gets an SBS long-term performance. It needs elasticity at year 20 and year 30, not just at day one. So I think that's a key. Formulation is key, no matter what. And I think what you're going to see next in the next video that Min's going to talk about is PMMA, and it's a little different, but it's still formulation is the key.
Yep. And now we're going to transition over to PMMA, and you will notice QC for PMMA, like Kirk said, it's a little bit different, but formulation is just as critical.
Hi, my name is Min Nam, and I'm an associate chemist here at Siplast, and we're here at the RISE Center. So here at RISE Center, we also run a lot of lab batches, and after each lab batch, we have to run the QC. So here I have a batch of PairPro. Very first step usually would be to bring down our sample into a desired temperature around 19 to 21 degrees Celsius. And you can see it's right at 21, so I'm gonna give that a go. And after that, we would test the dispersion of the resin to see if it's dispersed correctly, make sure we don't find any big chunks of particles in there. So I'll just scoop a little bit of it into our glass plate and just rub it with a little bit of pressure. If there was any non-dispersed particles in there, you would see big streaks that's happening. This test basically does something similar. It's also testing the dispersion. It's Hegman gauge, put a drop of it on the top, scrape it down to make sure it passes the dispersion number. So we can see where it breaks off would be the number we record. So the dispersion looks good. So now we're going to test viscosity. So for PairPro, we use our hockey viscometer, and we use our spindle 1. So I'll just lower it down until this line. And I'll just go ahead and start. And the spindle will just spin and measure the viscosity, and then the number will be displayed on the screen. And once that's done, we would go ahead and measure our density using our density cup. We first have to tear the empty density cup to make sure how much that weighs, and then fill it up with our resin. To make sure it's all filled in there without any air bubbles, we will close it with the lid that has a little hole in the center. Put the cup into the scale and record the final density. This is our moisture analyzer to test how much of a solid content we have in our resin. We put a little bit of our sample in there. We close the lid. Then once we start that, we pull down our hood to make sure it gets vented. And it basically would get heated up, and it would dry out the sample until the amount of solid content is recorded. This is the PairPro sample, and it's already catalyzed in. And for PairPro, we would mix in 2% catalyst. We would mix for about a minute and a half. Draw down. And then we want to check back in an hour to make sure it's cured. That's what we're looking for, the cure time, to make sure it's a tack-free cure. And once it's cured, we would also take it to our colorimeter to measure the color, and just to make sure they fall within the spec of our color spec.
You will see Min again in some of the next segments of videos we have, but her main responsibilities are for liquid R&D and raw material qualifications. Min is a chemical engineer out of NYU, and I really need to applaud her and her colleagues for their work with raw materials this year. As you know, supply issues have plagued our industry, and Min's raw material work has kept our liquids business really on track.
It's really eye-opening to see the significant amount of effort that goes into what her team's doing in terms of checking the raw materials prior to these batches even being made. And the time that Min and her team puts into this formulation is really leading to the superior performance that we've all come to expect of Siplast.
It's a big difference on the PMMA side. Our SBS side is 3, 4 components. Our PMMA side is 20 or 30 components. So, and in little quantities in many cases. So a lot of this testing that Min is doing is really about making sure the product that the contractor gets is very consistent. It is a more chemical, formulation versus bitumen that is a little bit more natural, but it's easier in that regard. But the complication of the formulations really require that we do this really diligent, both raw material, evaluations prior, and then make sure that the batches are right, spot on. And that from a formulation standpoint, it's a little different too, because from SBS is typically covered in granules. For PMMA, it's going to be exposed to UV. It doesn't typically have a secondary covering, so we have to formulate a little different. Min's going to talk about aging here in the next video.
We're here in the RISE Center building, and here we are with the QUV accelerated weathering tester. And this unit is really special because we get to look at accelerated weathering that happens outdoors at a shortened time. You can see we have 4 lamps on each side. Our company focuses the use on the UVB lamps because it focuses a lot on the shorter wavelengths, which impacts the color and especially the degradation in the polymer. It focuses a lot on that. It helps represent the very aggressive condition out there. And we want to see how our samples react in these aggressive conditions. It's also able to control the condensation method or the water spray method that happens in the units. And for our test, we focus a lot on the condensation, which represents the dew that happens in the morning of the weathering, which usually is the biggest factor that encounters when the weathering happens on the samples. You can store them in different sizes. There's a smaller one to medium to a large sample holders you can place them in. It really depends on what kind of test you want to run with them after you remove the samples as well. For example, the bigger ones, we can always remove them and look at its physical properties, how the aged conditions impacted the physical properties of the samples. Whereas for the smaller ones, they're mostly focused on the color degradation and how the color changed over time. We already have this sample out here that's been aged for about 2,000 hours, but we're gonna put it back to run additional testing. You can tell from the 2,000 hours how the samples changed from the colors got a little chalky or yellow, or just from the visual representation, that's how it looks. So I'm just going to put it back down, and we always want to have it face it downward because the lights are on the inside of the unit. And we would have a back holder to have it pressed down onto our panel. So we would secure it with some rings. So I will write down the sample ID, the date I put in, or the hour it starts. So you can see the hour it starts from the front screen. We would write down 69:20 as our start time. So I will place them in there, secure it with a holder on the side just so the lights do not escape when we turn on the light. So they can be stored at a certain temperature. So I'll just close it and start the machine. We normally leave it for 1,000 hours, 2,000 hours, and 5,000 hours. And 5,000 hours would be our very extreme condition that we want to look at.
So as Min was demonstrating the aging characteristics of PMMA, it's aged differently, and it's aged in a QUV oven, whereas liquid applieds do not have protection on the surface. SBS does, and so it's aged in a dry heat oven at 90 days at 70 degrees C or 45 days at 80 degrees C.
We're always asked about what the comparison of artificial aging and Mother Nature is. And really, there's several guesses out there, but there's no clear answer. Outdoor exposure changes second by second. And the only clear way to compare it is to look at outdoor samples versus what you've artificially aged. And one thing we encourage our scientists to do, whether it's for mod bit, whether it's for PMMA, any sort of product, we encourage them to get product outside, get them on the roof of the plant, get them on the roof of the RISE Center, get them on the outdoor exposure racks, because that's the only real telltale way we'll be able to see what Mother Nature can do. And for our Siplast liquids in particular, we have over 20 years of proven field experience with our products. And as you just saw, we formulate to withstand outdoor aging in Mother Nature, as I said, but we also formulate for what is needed from an application standpoint, which Min's going to go into next here in these videos.
This is a gel-norm gel timer that we use to measure the time it takes for our resin to cure, or not fully cure, but get into the gelation form. So the time we get here typically represents the pot life of the product out in the application world. So that time spec we have is basically how much they have in order to be able to apply them before they start curing inside the pot. So here we're gonna step through working the gel timer, the gel-norm gel timer with Pro Primer T. I already have it measured out here. And so for primers, we would add 4% of the powder Pro Catalyst. That's what I'm gonna do right now. And once that's all in, I'm going to start mixing. And I will start my timer to make sure I mix all of them within time. And generally, I would mix it for about 10-15 seconds. And once I have enough, it really depends on the product and how much you put on, but it's basically a little bit above the water line. And I'll put in the unit, make sure the stamper is clamped on. Basically what it's doing right now is we have our resin in the test tube underneath mixed with the catalyst, so it starts catalyzing, start curing, polymerizing. And the stamper on the top is just moving in an up and down motion, making sure it's getting mixed at a constant speed. And once the gelation happens, the stamper gets stuck in the resin and pulls up the test tube, blocks the light, and therefore stops the timer. And we would want this range to be around 9 to 11 minutes for this specific product. And for this test tube, we also keep it at a temperature of 20 degrees Celsius, just to mimic the ambient temperature, the normal room temperature, the ambient temperature we typically look for. We always test QC at the end of the batch. So once they're done formulating, we would check once. And if everything falls within the spec, that's good to go, and we would package it. If it falls just a little bit outside of the range, we can always make a correction into our formulation. So we would either add the accelerator or the inhibitor, depending if the gel time is running short or long, and let the production line know, and we would make the correct adjustments. And after that, we would run the QC again to make sure they fall within the spec. So here we have two different formulations that we're going to compare the rheology properties. How we're going to do that is using this anti-sag meter tool that we have here. And each section represents different thickness. So we're going to see if it passes the anti-sag test, and if it fails, at which thickness it fails. So just going to put it down, pour a little bit of our product, and pull it down. Now I'm going to do the same with our other product after cleaning it. Okay. I've already put the tapes on the little paper so we can hang it on the wall. That way we can see if they would sag or not. So as you can see for this product, we're seeing the flow around like 30, 40 thickness compared to the other one. We don't see a flow. When we're doing a vertical application, we would want the product to not flow. So as you can see, we're comparing two different rheology modifiers here, and we see that one on the right serves its purpose better. We would not want to see a flow like this on the left. This is what we see in the outside application when we try applying it on the vertical surfaces. For the ones we apply horizontally, it's okay if they flow at a certain thickness.
So as you can see, Min's demonstrating some of the characteristics you would look for in the field. But what's really important, and with a strong background in application, is for me to take the scientists out of the lab and put them in an application situation. And it's important when they see how that product's used in the field that they can relate that back to the lab. And you see a light bulb just go off when they're out in the application center with me, actually physically putting down the products.
Todd, it's so important for our scientists and chemists to be hands-on with our products so they understand this real world application and the real world challenges that we face on project sites, from elevated surface temperatures to wind-blown debris to dramatic temperature swings throughout the day, and how the materials are impacted by these ever-changing conditions, like Zach said, moment to moment. But it's equally important for our designers to understand application and seeing firsthand how material can set up on a hot summer day, or how difficult it can be to keep that liquid applied material running down the wall. It really just helps improve their understanding and the way they write specifications and manage detailing, as well as understanding the challenges that might arise from the project site during construction. And I think I got a lot of that when I actually was invited to the plant tour as a consultant and really got to start touching and playing with these materials in real time.
Yeah, and you notice with the tests that she was doing, they were pretty simple tests. The gel norm, looking at the gel time, and then doing the anti-sag test. So, really telling us what the contractor is going to have in their hands. Looking at the gel time of the product, how long they're going to have for a cure, depending on whatever the substrate conditions are, or whatever the temperatures are. But for the sag, once again, very, very simple test, just an easy draw down. You invert it for 24 hours, and you see what kind of sag you get from your product, whether it's at 50, 40, 30, or 20 mils. So, and you can see how that related to when we went out to the roofing school and did some hands-on application.
Every incoming scientist, you really try to instill in them, hey, you can't formulate if you don't know how it works. And I think that's the tough part. And I think you get blank stares sometimes when you get somebody right out of college, because they weren't taught that in chemistry lab. But it's a practical business, and I think kudos to all of our scientists, because I think they enjoy it as much as anything. They enjoy when they're wearing the lab coat in the lab, but they also don't mind getting outside and doing the real application of the products. And I think that's what makes the difference in our scientists versus others. Now, we talked quite a bit about PMMA, so I think we, being an SBS diehard, right? We're gonna slip into some SBS here and talk a little bit about the product that got us started 40 years ago.
Hi, I'm Luke Jeffreyon at the RISE Center in Siplast. So today we're here at our dynamic shear rheometer. It is a parallel plate geometry. So basically you're taking two plates, or two basically like pieces of bread, and you're basically sandwiching them, putting some jelly between them, and then just turning it and kind of seeing how that affects the properties that are inside the jelly. And so we do this for all of our modified bitumen blends. Modified bitumen is basically just an asphalt and polymer together, and that gives us our kind of waterproofing and elasticity that we need. So by adding the polymer into those blends, we end up getting, that's how we get our elastomeric kind of compounds. So that's how we get the long elongation and things that we like out of our products. So we load our samples in these molds. We pour hot bitumen into this. We're going to take it, and then we're going to set it into the DSR here. We're going to press it down, just make sure it's kind of centered into the end of there. And then we're going to raise the temperature of that to about 90 C. And we're going to let that heat up. Now this is stopped, we're going to go ahead and trim off the excess part of this. And so we're just going to trim around the edge. And pull, and you can see the nice elasticity that we used to have out of the blend there. Real good stuff. So one of the things that we do with the DSR is to assess the elastic properties of our modified bitumen blends. And so we do this through a physical property of the material known as the elastic modulus. And so this elastic modulus, generally we want to be in a defined range that works good for us. And so one of the things that we notice that as the blend ages is that this modulus tends to increase. And so as this modulus increases, that means that the material becomes more brittle and it becomes harder. And so as bitumen ages, it becomes oxidized, and so it becomes more brittle and it becomes easier for it to break. And so one thing that we need to do with modified bitumen though is to be able to mitigate those effects. And so we mitigate those effects by basically lowering the filler content that's in our blends and then actually increasing how much polymer that we have in there. And so basically making sure that that polymer can last for a really, really long time, and so that we have really good elongation properties 30 years down the road.
So it's really nice to see analytic testing to this degree from the building science perspective. I really appreciate how Luke talks about mitigating risk by using materials that are designed to maintain elasticity 30 years down the road.
I'm sorry, Jennifer. Did I hear Luke use jelly and bread as an analogy for the DSR?
Come on, he put it in layman's terms and gave us a really great visual on how these tests work. Everybody was able to picture that.
Yes, I agree.
Sometimes it's the simple examples that are better. The elastic modulus of the material is really, to your point, Jen, is, I mean, the analytical parts of it. This business, the roofing business, has been very dominated by basic testing of finished products and very simple testing. But I think the future of roofing and SBS and PMMA and all the other materials are really more of the analytical science and the deeper dive into the material properties. And I think we can really do a lot more today than we did almost 25 years ago when I started here.
And I want to make note, Luke has his master's in applied physics and he's working on his PhD. So he was just dumbing it down for people like me, saying jelly and bread there. But, you know, one of the things that I really enjoy about Luke is he's not afraid to ask a question. He's very eager to learn. He's always knocking on the door asking, hey, what can I do next? What can I learn more of? And he's proven to be a great addition to our team. So like we talked about, Luke showed you how to evaluate the modulus with the blend itself, with the SBS blend. Now let's show you how modulus and elasticity look like in a finished product. Hi, my name is Zach Taylor. I'm the Research and Development Lab Manager here at Siplast. We're here at the RISE Center with our tensile testing unit. What we can do with that is apply a tensile force to a sample, and we can measure the tensile strength of it and the elongation of it, as well as several other properties, the peak load, the ultimate elongation, the max elongation, tear strength, several different properties we can look at using this unit for modified bitumen roofing or for some of our liquids materials. I have a sample of Paradigm 20 TG. It's one of our modified bitumen base sheets. This has a fiberglass reinforcement in it. So I'm gonna load the sample into the unit here. 2 sets of jaws. When I start my test, these jaws will begin to separate at a predetermined speed. This is for ASTM D5147. So we're gonna come over here, zero out our force, and start the sample. The reinforcement's been broken, so this is all elongation of the product, of the blend that you're seeing. You can see that nice amber color of the blend, and that's showing the elongation of the blend itself and not the fiberglass anymore. So here on the y-axis is where the force is measured that was applied to that sample. So here we can see this is the break point, or where the peak load, the tensile strength is reached right here. That's where the fiberglass broke, and that's what we're seeing here is the peak load. And what you're seeing here now is the graph is starting to drop down. We're losing that load. And what we're picking up here now, this is the elongation. So this is our x-axis. We're measuring this elongation at this point. Elongation at peak load, what that is really what it says. It's the elongation that's reached, the stretch of that product. So for this sample, it is the fiberglass. So that's how far it stretched up until it reached that peak load. So there's your elongation at peak load. Another critical point outside of peak load is the ultimate elongation. Ultimate elongation is measured after you reach 5% of the peak load. So here we've had the load has been decreasing down, load's going down, and that measurement is not taken until we drop below 5% of this peak load itself. We define ultimate elongation at 5% because there's a lot of things that go on right at the very end of this test. But once again, we're still seeing that nice amber color all the way throughout. Here we've dropped below 5% of that peak load. So that's where our ultimate elongation was recorded. We formulate so that we have a high elongation, ultimate elongation in the very beginning. So the product that goes directly on the roof, we have a very high ultimate elongation. And we know that when we install that product and it sits there and it goes through UV exposure, heat, cold, all the movement of the roof throughout the lifetime of that roof, 20 plus years, that we know that we're gonna have enough polymer based in our formulation that we're still gonna be able to have this pull back and forth, this ultimate elongation, the blend elongation as I like to call it, of the product. So here we have a competitor base sheet product. This has got a fiberglass reinforcement in it. With this product, it's got a higher filler content, lower polymer content. If you watch here, start to apply the load, we're going to see that reinforcement, it's broken. Seeing a little bit of elongation there, but as you can see quickly, we're starting to see that blend tear. Now we're at about the ultimate elongation point. This product, we got 4% elongation just with the reinforcement itself. So the blend was only about 4 and 14, so about 10% blend elongation, ultimate elongation around 14%. The more filler you have in your blend, when you go above 30%, when you go above 40% filler, you've essentially gone from an elastic membrane to more of a plastic. So you're going to have a more rigid membrane. You can kind of see that in this product itself. It's a lot more rigid. It's not as flexible, and that's because it has a higher filler content. If you don't have a high enough polymer load in the beginning, we know it's going to degrade. It's going to degrade quickly, and you're not going to have that polymer to allow for that elasticity throughout the lifetime of that roof. So once you reach around that 10, 15 year mark, you don't have enough elasticity in your blend to overcome that substrate movement, to overcome the movement you have at multiple times a day when the sun's at the highest point or when it's cold at night. So here in my right hand, we have our, this is our Paradigm 20 TG, our fiberglass SPS base sheet. In my left hand is a competitor fiberglass base sheet. If you look really close here, we use a lot finer sand for our surfacing, for our parting agent for our products. And what this does is, using this coarser product, it displaces asphalt. So it cheapens the product. It allows it to, you can still get that desired thickness for ASTM or desired thickness for your finished product. But what you're doing is you're cheating the customer because you're selling them more sand than you are actual blend.
All right. We had to apologize to everybody. We had to call in the B team for that video. Sorry, Zach. I'm just kidding. Now that's a ultimate elongation. If you've been to if you talk to any Siplast sales guy or anybody in our group, ultimate elongation is really what we preach. And the reason I wish you could put, when you see that video and you see the elongation, it means so much more than just a number on a page. It really is, when we talk about elasticity and how the product works, it really is the key to understanding those types of properties. And we didn't do polyester in there. Those curves look a little bit different, but in reality, it doesn't really matter. You should still have 40 or 50% elongation past that reinforcement break. It doesn't really matter. It's a really good indicator of how good quality that blend is, and that's what we're always looking for.
Yeah, Kirk, you're right. And as great a test as that is for testing our products for QC, we've also started a competitor program in the early 90s using that same test as a benchmark. And it was extremely eye-opening to see what our competitors were doing as opposed to what Siplast was putting. We knew we had a good blend. We knew we had a good product. But that first competitor test that I happened to be a part of just really showed the difference between the competitor and Siplast.
And the greater that elongation, the more stretch that's available in the membrane, which is allowing it to move with the natural expansion and contraction of the roof system components. So again, just taking everything that's going on in this RISE Center here and applying that to what's happening in the field. And that's why we're digging into the quality and really looking at all these elements to apply it to that real world performance.
So SBS really, you need a good bitumen. That's the base of what you need. But SBS and the performance of the SBS, the life of the SBS through the roof is really the key. Elasticity is the key. It's helps hold the granules. It helps react to those movements on the substrate. It really is the key to holding everything together and making sure that you protect that bitumen and you get a long life, great cyclic fatigue performance even at year 20 or 30.
The glue that holds it all together.
That's right. The rubber that hits the road, or where the rubber meets the road. Sorry.
Hey, we got a question that came in. I think it's a timely one here. This is from our own Rob Worthing. Does the ultimate elongation differ depending on ASTM 61, 62, 63, and 64?
Yeah,
Kirk, I'll throw that to you.
Yeah, I'll take it. I mean, really, that's the difficulty in comparing polyester and fiberglass, because if you said one was 50% and the other one was 50%, I really don't care what that number is, just like you see in that video. Even if polyester is going to stretch 40, 50% before it breaks versus fiberglass, which is going to load up early, and then you're going to see that blend elongation after it breaks. you're going to see that same elongation after a polyester breaks, even at 40%. If you look at our data sheets, we're going to have 80, 90, 100% ultimate elongation on a polyester sheet, because we're still going to get 40 or 50%. What you want to look for is that difference in elongation at peak and ultimate elongation. If those are close, 5, 10% difference, then you're not getting much elongation after that reinforcement breaks. So there's a lot to it. You have to be careful with those data sheets. It's an important thing to understand. And I think, again, this is a great test to tell you the quality of the blend.
And, the question we get to is, how do you know? How do you know you've got that elongation for up to 20 years? And one of the great things we do here at RISE is we do what we call roof cut evaluations. And what that is we have our sales and field, they go out, they test roofs, they get test cuts from roofs, whether they're coming at the end of their warranty, or maybe they're having an issue with the roof itself, or maybe it's a competitor roof that they want to see about overlaying the top of it. And what we do is we're able to break those roofing assemblies down, evaluate them, see what the condition of them is, and give them the recover and guarantee options that they need. So before we segue into our next video, our next guy here it's Tyler. He's going to go over the RCE process. Tyler's been with us for around 10 years now, he was with an environmental lab for about 10 years. And that work experience has been helpful, but he's really become our go-to person for application work and testing. And he also gets the honor of being our champion for our hail testing. So he's always destroying stuff with our hail cannon. So let's see what he's got to say about roof cuts.
My name's Tyler Day, and we are at the RISE Center. Today we're going to be going over roof cut evaluations, how to analyze a roof cut when sent in, whether it's for warranties or an issue with the system on the roof. So our field team, they'll go up on a roof and get some roof cuts, and then they'll send them to me, just like this, in a box. They'll typically come with the information that I need on what the system is, how it was put together with maps, and then labeled. So they provided all of that for me. This tells me where it was from, the job number, and then what test cut it is. This will have the age of the roof, whether it's a torch or an adhesive or anything like that. This is a Paradigm 20, Paradigm 30 torch roof. It's 21 years old. This roof cut here, it has great granule retention. I don't see any voids or loose corners, nothing where I see where moisture was traveling through. So this is a really, really good roof for its age. We're going to find out if it's going to be a great candidate for a recover. So from here, I will take a picture of the cap sheet, and I will then take that picture and put it on my computer, and then we'll do a phase analysis on the granules of the cap sheet, and then we'll see how much granule loss in percent that we have. Also, we'll do cross-section cuts on it as well with the microscope. Okay, so once I've taken the photos of the cap sheet and I want to analyze the granule loss, I've put the photo on the computer. For granule coverage, you're going to want to do the phase analysis. And the way that works is it's going to depict the difference between the granules and the bitumen. I'm going to go into phase analysis, and then this is where I edit thresholds. So it has automatically covered up what thinks it is, but you really want to be careful and to make sure you're not covering up any granules that happen to turn black. So kind of scroll down the chart. Once you have all of the bitumen highlighted, that's where my set point is, and it's going to go through and analyze this image, and it's going to highlight it. And then so I'm going to save this image, and then it comes out and it tells me this granule coverage has a 20.44% loss. So I'm going to say it has an 80% granule coverage still on the cap sheet. Now we're going to perform a cross-section cut. Typically what we'll do, we'll cut down this side. Now that we have our cross-section cut, place the sample underneath the microscope. We're going to take a photo of it. Right here we'll see that we have our Paradigm 20 and our Paradigm 30. This is a torch grade material, and it is fused together, and you can see a slight line, but there is no distinct extra material in between the two plies with each other. They are fused together. Unlike an adhesive sample, where you would actually see the extra material in between the two plies together, and that's what we would measure on an adhesive sample. So once all that is done, all of the cross-section cuts and measurements are done, I typically have someone in the field get me a Google Earth image of the building that the roof cuts came from. And then they'll go on there and they will mark and number where each cut was taken, as for numbering the samples as well. That way we know exactly where those samples came from. If there's anything distinct about that area, we can cover that in a much better way. So then once all that is done, I'll go in, I'll have it marked where it is, and then we should have all of the information to generate a report from granule coverages to photos to cross-section cuts.
So talk about a true partnership, utilizing the RISE Center and Tyler's experience to assist our customers, helping them to evaluate their existing roofs to determine if it's a candidate for a re-roof. And by the way, the 80% granule coverage for a 20-year sample is really impressive. But analyzing these samples from exploratory openings and then combining that with the visual assessment and the moisture survey, Siplast is truly there every step of the way. And although Kirk has more gray hair, we've been jabbing Todd on his tenure today. So Todd, surely you have some good stories. How long have you been assisting our customers with roof cuts?
Thanks, Jennifer. Yeah, that seems to be the theme today, is my experience. But I remember the first roof cut, and it was years ago. And there's a lot, like Tyler was showing you can learn a lot from these roof cuts, the granule retention, the application. What's a better application? Cold adhesive, torch, hot asphalt. And we took it a step further with the recover program. We can analyze the product if it's a candidate. And we've done this with 10, 20, and 30-plus-year-old roofs, and we found there's 30-plus-year-old roofs that are still servicing well. But if the customer's looking for an extended warranty, like in the case Tyler's roof cut he has, we can analyze that roof and see if it's a candidate for maybe a direct overlay in adhesive, or peel the cap if it's hot applied and put a Paragon 40 in adhesive. So Siplast offers a recover program for the customer to continue that partnership.
I'm not so sure about that gray hair comment, Jennifer.
You're right. I haven't seen you in person in a long time, but could just see the shadows.
No, Todd's right though. Just to hit on that. I mean, I mentioned when I first started, Todd, took me under his wing and taught me everything about roofing, because I knew nothing at the time. But we've done hundreds of these roof cuts over the years, and it really helps with knowledge and understanding. And I doubt there's really anybody out there to compare to that kind of knowledge from a roof cut basis and knowing just what our products do over the years.
So I just want to start out by thanking my entire team for making these videos. Kirk made the comment about the B team with my video, but folks, I was there for 3 hours in front of that machine, and there was only 2 minutes of video. So the rest of my team, they were champs. They were pros. They got it done quickly, but I completely blacked out. So, but I wanted to mention too, we also have other scientists on staff that are key players in the success of Siplast R&D. They weren't included on the video, but I wanted to give a shout out to them. And thank you today for everyone joining in, and thank you to my co-presenters for helping with this.
And we hope to have you here to visit the RISE Center and be a guest at one of our plant tours, hopefully in the near future. Like I said, I was fortunate enough to participate in the plant tour experience as a consultant, and now I get to join you on the other side. So looking forward to
that. Just to follow up, just thanks to everybody for tuning in. We're very proud of this facility, very proud of the people that work there and the work that they're doing to improve Siplast and our quality. And I want to thank, the scientists. It is, like Zach said, most scientists are going to be introverts at heart. So getting in front of a camera is not their favorite thing to do. So, but they were great sports and did a great job. And thank everybody. Thank Laney for running it and the presenters. And like Jen said, I can't wait to get you there in person. And when the world changes a little bit, get everybody in person and enjoy the facility and enjoy some time together.